Audio recording for this meeting has begun.
So again, good morning, good afternoon, everybody. If you're watching us via the recording, hello and welcome. Before we get started, I'd like to give you a little bit of a brief introduction to today's session, as well as tell you about our three presenters. Today's topic is evaluating the accuracy of smartphone-based travel behavior data. We have three presenters joining us. Our first presenter today will be Mr. Sean Barbeau. Sean is the principal mobile software architect for R&D at the Center for Urban Transportation Research at the University of South Florida. His research interests include multimodal mobile apps, open source software, standardized open data, cybersecurity for mobile phones, and transportation infrastructure. Dr. Barbeau holds a BS and an MS in computer science from USF, as well as a PhD in computer science and engineering from the University of South Florida. Additionally, he will be joined by Sean Turner. Sean is a senior research engineer at Texas A&M Transportation Institute, where he has developed, conducted, and managed applied research for 29 years. Sean is nationally recognized expert for practical experience in multimodal travel data collection and analysis, performance measures and monitoring, and mobility analysis. And then finally, our last presenter today will be Wilson Lozano. Wilson is a computer science and engineering PhD student at the University of South Florida. He has been a research assistant at the Center for Urban Transportation since August of 2020. He works under the direct supervision of Dr. Sean Barbeau, and his research, he's currently conducting research on activity recognition based on travel behavior data. And with that, I'm going to hand the presentation over to Dr. Sean Barbeau. So Sean, take it away.
Thank you very much, Stephanie. So today's project, although it's myself, Sean Turner, and Wilson Lozano joining us today to present, this is part of a larger project between a collaboration between TTI and Qatar. So thanks also to Michael, Trang, Robert, and EPEC for their contributions to this project. So an introduction to the problem here is so multimodal transportation is vital to livable communities, and so all modes of transportation really contribute to the overall travel picture. So that includes transit, bike, walk, ride sourcing, so Uber, Lyft, car share, and bike share as well. So the traditional data collection techniques to understand multimodal travel behavior have limitations traditionally, but they've been focused more on single modes. So in the past, it was fairly easy to throw a GPS unit in a car and track the car traveling around a city for extended amount of time. This gets to be much harder when you're trying to track individual riders because you're dealing with something that's ultimately portable and has to travel with the user, which then has battery life limitations. So things looking at a single mode like onboard travel surveys miss those non-transit riders. So the transit rider that may have decided to take Uber or Lyft for a particular trip instead of transit, you miss out on that. And activity diaries and surveys have typically been time limited to a few days, and this is because of just the manual burden on the traveler that has to fill these out. So pencil and papers, the lowest tech version maybe to do that. So mobile apps have been built in the past specifically for travel behavior surveys. One thing is that these apps that are specifically designed for travel behavior surveys, there's difficult user acquisition. So you have to go out and recruit users or have an established pool of users that you pay incentives or some type of motivation for them to participate. In the past, you have to be very careful with negative impact on battery life when you're tracking users. I think anyone who's used GPS on a cell phone for an extended amount of time can relate to that. It tends to drain your battery relatively quickly. Although modern apps perform better, and I'll talk about that more in a second. So it can be hard for users to remember to manually start and stop recording if the user is responsible for doing that. And then for proprietary apps that have been designed specifically for travel behavior data, often this data comes in a black box to the researchers. So you don't really get to see the underlying nitty-gritty raw data. You just kind of get an output of this is what the app collected, and you don't know what potential biases might go into that. So these issues can all prevent a better understanding of real-world challenges in this area, multimodal travel behavior choices, and relationships between travel behavior and health, for example. So a previous National Center for Transit Research project was conducted from 2018 to the beginning of 2020. And if you're interested on the deep dive of this project, there is a final report and a webinar that you can dig into. I'm going to cover this at a very high level at the beginning of this presentation because this project is what built the tools that we are using to analyze the data in our NICR project that's ongoing now. So the app that we're using for this data collection is called OneBusAway, and this is an open source platform for real-time transit information. It's supported by a nonprofit, the Open Transit Software Foundation. And this nonprofit includes members of transit agencies, universities, USF, myself. I'm a board member for this nonprofit, and other consultants and independent developers. It's been deployed by agencies in 11 cities worldwide. And agencies see advantages to pooling resources to be able to deploy a platform that they have some level of control over versus embracing third-party apps, which can make their own decisions and how they choose to show information to riders. So pre-pandemic, there was an extremely large number of users. There's been over 1 million unique users of just the mobile iOS and Android apps, typically around 330,000 active users in the last 30 days. That's dropped during the pandemic, as has transit use kind of worldwide. So we'll see how those numbers pan out going forward. And most importantly for us as a university, this can be a platform for research. So there's been past research by other universities involved in the TSF that have showed the benefits of real-time transit information, and this then helps decision makers decide if they, show proof that these technologies do help transit riders and can even increase ridership. And we have direct control of the entire user experience, so we can do different experiments with users and understand how those experiments directly influence these users. And this is opt-in research, so users can choose to opt into these research studies. So in the previous project, our research team implemented the Android Activity Transition API in the OneBusAway Android app. And this uses newer hardware sensor coprocessors, which are very energy efficient. So this allows us to monitor the user 24/7, and then lower level sensors detect when they transition between activities, which then wakes up our app, and then we can capture data at that point. So this is the same API likely used by any other modern proprietary survey apps. So again, to be energy efficient and not kill the user's battery, we really need to rely on these underlying hardware-based technologies to do this efficiently. So this technology and the hardware is able to give us activity transitions to alert us to users that are in vehicle, on bicycle, running, still, and walking. And for each of these transitions, we get a confidence value between 0 and 100. That's the likelihood the user is performing an activity. So this is calculated by the hardware. And then after each transition event, we capture location data from 3 different location providers. So global navigation satellite systems, such as GPS, network-based location, which is cellular or Wi-Fi based, and then also Fused, which is a Google technology, which is, they do some sensor fusion to be able to produce what they say is a more accurate position. In addition to these activity transitions and location data, we also capture information about what the user saw in the app before they made these activity transitions. So this includes arrival times that they have looked at, including the delays and whether certain routes, what route they looked at and whether that route is running on time or ahead or behind schedule. Trips that they've planned, the origin and destination, and the different options that they were shown, including different multimodal trips. You can see a bike share and transit trip transfer from transit to bike share shown here. And then also if they set a reminder in the app to indicate that they want to get off the bus at a particular stop. So these are all interesting pieces of information that give you interesting context and knowledge about potentially why a user was making a certain activity behavior or travel behavior choice. So the raw data we get off the phone is a stream of events that would tell us that, okay, the user transitioned from still to a walk, and then there was another transition from walk to a vehicle, and then vehicle to walk, and then walk to still. And so we developed some software that's open source that anyone can use to transition from this kind of model of activity transition data to your more traditional OD trip representation. So a walk from one location to another, driving from one location to another. And we'll talk about this a little bit more later. So the output then of this software is a CSV file, so a tabular data that shows you in this format of trip from one location to another location starting at a particular date and time with the mode that was detected by the phone hardware next to that. And we also export a version of that data that can be viewed in tools like Google Earth, a KML file. So an example here shows the data that we captured from the phone is the green triangle is the start of when it detected a start of an activity, and that in a location associated with that start activity. The red circle indicates where an activity was ended, and a location associated with the end of that activity. And then overlaid on this slide, I've added a blue triangle, which shows my actual position here. So this is where I parked my car in the parking lot outside of Qatar, and then the blue circle shows my actual end location. So that's my office when I walked in and actually sat down at my desk. So you can see that there's typically a slight delay here, which we'll talk about a little more in a minute when we talk about some statistics that we've been running on trips and accuracies. But still, this is able to capture relatively close detail of what actually happened. So you can see that this particular location, we have an algorithm that picks like what we call, quote, the best location, which is a very simple algorithm, which we may look at improving later based on what we learned from this ongoing project. In this example, the GPS is what we used and chose as the best location here, which is ultimately really just the nearest location in time with the timestamp closest to the activity transition. And then at the destination here, it used the network, so likely the Wi-Fi network that's there at Qatar, and a position that's known and connected to Wi-Fi routers there to say that my activity ended at the red circle. So you can see that there is also a delay between when the activity transition is detected and we acquire a location associated with that activity, which is important to keep in mind that delay was very brief, 0.2 minutes at the start of this detected activity, and it was about 2.5 minutes when I got to my office location. So this proof of concept was deployed in July of 2019. It was rolled out to all the OneBusAway Android users. And so fast forward to October of 2021, and we've had over 13,700 users opt in to allow us to collect their travel behavior without any incentive associated with that. So we were excited about that, and that gives us, we've been collecting a lot of this data since 2019 across many of the different cities. So the primary user bulk is in Seattle, followed by San Diego, and then here in Tampa, and then Washington, D.C. is, I believe, not too far behind. So those are the main cities that we're looking at. And this wealth of data really allows us to better understand the raw data behind some of the modern proprietary survey apps. So we can see the exact stream of data that's coming off the devices, and how that kind of the techniques that have to go into manipulating that to transition it to your more traditional origin destination type information. And then also what's really interesting is that we can link that in-app usage information that I was talking about when we know what information the user saw before they went about doing a particular activity or chose a mode of transportation. And we can use and relate those two to do specific research. We can also reach out to the user. We have their email addresses, so we can do additional surveys and add more information in the app if we want to target collecting information for a particular study. But the big question at the end of this project was, how accurate is this data in space and time? We didn't do any sophisticated, extensive analysis to compare this against ground truth data of known origins and destinations when people were traveling. And then the question was, what's the methodology that we should go about doing that? How should we measure this information? So that brings us to this particular NICR project that we are working on with TTI. So the goal of this project, that you might have guessed, is that we are determining the accuracy of the activity transition data collected from smartphones via the OneBusAway mobile app. And again, this is OneBusAway just happens to be the app that we're using to collect this data. The data, any app using the similar API would see the similar type of data. And then based on this evaluated accuracy, we also want to determine how this data can be further utilized to assess travel behavior depending on the different accuracy requirements in time and space for different applications. So this is funded under the National Institute for Congestion Reduction, or NICR, and as I mentioned, partnership between USF and Texas A&M Transportation Institute. So with that, I'm going to turn it over to Sean Turner from TTI to talk about the accuracy methodology.
Well, thank you, Sean. Pleasure to be here. And so in our practice session yesterday, I promised Sean and Stephanie that we would do no more than 3 Sean jokes. So I don't think we've done any yet, but so it has been a pleasure working with Sean and his team from the University of South Florida in Qatar. So TTI actually does quite a bit of independent evaluations of different types of technology as well as different data providers. And so this kind of fell right into our wheelhouse, and it has been fun working with the folks. So in terms of evaluating the accuracy, what we were primarily interested in were the things that are shown here on the slide. So we want to know how accurate are the time and location of the trip ends, what Sean refers to as activity transitions, or they're known in the Android API as an activity transition. The other thing I'll note is that I know the slide says trip ends. If there are any transportation modelers, really I think probably a more accurate way to say this is tour ends, because one of the things that we're actually testing is whether this app can detect short stops, say the end of what we know in transportation modeling as a discrete trip. So anyway, that's a nuance. So time and location of trip ends as well as the mode differentiation. Sean showed that in an earlier slide. So whenever we think about, well, how should we go about evaluating the accuracy of this OneBusAway app? Well, so there are a number of things that we have to ask ourselves. And I think one of the first things we have to ask is, well, what factors could influence accuracy? Because what we want to do is we want to make sure that our evaluation design captures a range of conditions that would capture those factors that we think influence. And let me show you what a few of those are, and I think you'll get a better sense of what this is. So for example, if we want to detect different modes, we would hypothesize that, well, if you were going from a driving mode, an in-vehicle mode, to a still mode, that's a pretty severe transition. You're going from a faster speed to basically still. That should be pretty easy. But if you're going to a less severe transition, maybe you've locked up your bike and you're now walking down the street to an office or a place to eat. That's a less severe, and we wanted to see the accuracy and the ability to capture maybe these less severe activity transitions. Activity duration is another big one. I mentioned in the previous slide, one of the things that we wanted to test was, whether or not we could pick up short stops, or really, I think one of the challenges in travel behavior surveys is collecting some of the short walking trips. So we want to look at, and we included in our data collection, activities of differing durations. The other thing, obviously, you're using GPS, so you want to factor in urban canyons, which is a challenge for GPS and cell phones. But I guess Wi-Fi hotspots is on the other end. I've learned quite a bit from Sean. And so one of the things that he was saying was, hey, these phones can get really accurate if they are sniffing Wi-Fi hotspots. And so we made sure to get a mix of places in these different conditions. Another thing, time of day, and different GPS satellites in view, that could potentially affect accuracy. And so we did data collection at different times of the day. Another thing, again, that I didn't necessarily think of, but Sean and his team's background, they said, well, phone model isn't important because some of these less expensive phones, the quality of the GPS chip and processor isn't as good as the more expensive phones. And finally, the last thing that I wanted to mention on that slide, if I can go back, is, okay. The last thing that I wanted to mention on that previous slide was other apps' use of location. In other words, if Google Maps is pulling your location and has the GPS chip fired up, then it's very likely that OneBusAway is going to be able to get a location read much more quickly. So again, we wanted to control and test for that. So those are some factors that we considered in evaluation design. The next thing that we had to think about was how do we collect this data? How do we evaluate it? Are we going to recruit some of the existing OneBusAway users? And Sean mentioned there's tens of thousands, if not 100,000 OneBusAway users already using the app. Or are we going to do more controlled testing by the research team that tries to replicate those real world uses and users? Well, as we were talking about what approach to use last year, the pandemic sort of made the decision for us. And so given the drastic travel changes, we decided that the best way to do this was to do controlled testing by the research team. The other thing that we had to decide is, okay, if we're going to do controlled testing, we need to establish a ground truth measurement. Essentially, we need to know, we need to have an independent device that tells us this is an authoritative time and location measurement. Because essentially what we were going to be doing, this is, the picture on the right here shows the TTI phones, and South Florida had a similar number of phones that they were carrying around because, again, we're testing different models. But what you see on the right-hand side is one of the things that we used as an independent ground truth. It's essentially two separate GPS loggers that are continually running and recording time and location. The other thing that we did during data collection, again, we sort of had a redundant system. So we had two separate loggers that were logging time and location, but we also made our own notes whenever we made the activity transitions, whenever we went from a walking trip to driving and so forth. We would essentially take a snapshot of the location with our phone, and that way we had a timestamp of when we made that exact transition at that exact second. And so fundamentally, this is what Sean had showed you earlier. Fundamentally, this is what we're trying to get at. We're trying to get at what is the accuracy, or what is the time and location or distance error between when we actually made an activity transition, when we parked a car or when we parked a bike, and when the app said, hey, this new mode, this new trip began in this particular mode. And so that's what we were after. So here's what we did. Given all of those different factors, here's what we did in terms of designing the evaluation. We did repeated multimodal tours. Again, these are tours in the transportation modeling sense, where we combined what I would call real world tours. We walked to the car, and then we drove to a location, and then we basically simulated walking to an office or walking to a place where we would sit for 10 to 15 minutes and dwell. And then we would essentially walk back and repeat that trip. And we did these multimodal tours at different times of the day, and we did them repeatedly And we used different modes. We did biking and walking. And in Florida, more than in College Station, they were doing transit trips as well. So we included different lengths, and we included minimum lengths for the different activities. And then again, the research team members that were carrying around these 5 or 6 or 7 different phones, they were also recording the activity transitions independent of those 5 or 6 phones that we had. And in sum total, we are testing 10 different Android phone models, again, because we want to look at the range of GPS chip quality. We're seeking urban canyons, and we're trying to avoid dense Wi-Fi hotspots, which, you know, if you're around a university campus or other downtown areas, you tend to get more of those Wi-Fi hotspots where you could have more accurate results than you might be able to get in other places. And the other thing that we did was we tried to control the use of other app location services. Again, we're trying to replicate real-world uses. So we want to essentially allow OneBusAway to take the Android API and fire up the GPS chip without other apps already having that GPS chip up and ready to report location. This is an example of the ground truth data that we collected. And so you can see here, we've got different multimodal trips. We've got different modes, dates, times. I've blacked out the latitude, longitudes, but we had exact latitude, longitudes. That's what we're calling our ground truth. That's what we're going to compare essentially against 5 or 6 other independent measurements from these 5 or 6 different other phones that we had both in Texas as well as in Florida. With that, I'm going to turn it over to Wilson.
Thank you, Sean. Can you hear me?
Yes, hear you fine, Wilson. Go ahead.
Okay. Thank you. Thank you, Sean, and Sean, for the context. It really helped me a lot to explain what we're doing. So now we're going to turn to the preliminary data analysis. So first, now we know that we have 2 data files. One includes the ground truth data using the format as Sean explained before. And we have one OBA file. There's a CSV file with the exported data from OBA. That the format is the one that Sean explained before Sean. So basically, what we're going to do with this, we need to know if the data from OBA behaves well. Then we need to do first a short algorithm or a simple algorithm to clean the data. That's pre-processing. So we do pre-processing on ground truth data, which is basically, for example, verify that data formats are correct. We are going to work in UTC timestamp, so we need to check the current data and translate it to UTC. That's the second part that generate columns. This data from timestamp for activity start is going to be used to look for a match in the OBA data set, the exported data set from OBA. And we also are going to remove the values that are not available, so not a number of timestamps if there is some, for some reason. Sometimes the collector cannot record the data. But that's not the case in this particular case. We are using the whole data set from ground truth data. On the side of OBA, then we are going to do a little bit of cleaning by dropping trips observation that doesn't match the time duration and distance requirement. So by previous observations, we decided that we are going to drop, for example, records of activity transitions which time duration is less than 2 minutes. Those are too short in time. And also we're going to drop observations or records which distance threshold is less than 20 meters. And also we're going to remove those timestamps. So after this process, or pre-process of these 2 data files, we're going to do the merging. So what we are going to, this is a preliminary data analysis, so we are going step by step. The first thing, we define a match. Our first definition of match, we're going to improve that later, but our first definition of match is going to be for each record on ground truth data, we're going to find one record on OBA which matches or have the same activity mode and have the closest activity start timestamp. So if it's on bike on ground truth data, we're going to find the closest activity start on bike from the activity from the OBA exported data for each of the cell phones that are collecting data. I'm going to explain about the collection cell phones in next slide. So we're going to verify. Sorry, need to change here the next. This is the merge. Well, I was talking about the merge. I didn't change the slide. I'm sorry. So basically, this is what I'm going to do, and we are going to use a threshold. We are going to find the part B. For example, if we the ground truth activity start data start at this point in time, we're going to define a threshold, and if we define or find a OBA activity with the same activity data type or mode between the activity start time plus the threshold, then we are going to define this as a match. That's is our fair definition of a match. So the description of this initial data set to this initial analysis, we have 3 devices, as Sean mentioned before. We have 3 collectors and 37 trips. For this, give us a total of 222 trip records. So what is one observation? One trip can have many observations, you know, when there are transitions. So basically, every record corresponds to an activity transition. Similarly, the OBA data have similar transition, but we have more records because the trips are recorded in parallel by 6 cell phones, and the records are according to what the cell phone detects on the user. So we are going to have 1,834 trips or records detected, but as we can see in the table on the right side, originally this is the number before processing, or the original, but after dropping the short trips and distance and time, so we have a reduced number of records. So we went to roughly 1,800 to roughly 1,300 records. Okay, so I'm going to go a little fast because we are running out of time, but yeah, well, we're going to do the preliminary data map analysis. So we're going to do an analysis on matching rate. Which is a matching rate? It's how many matches I found for the total ground truth data over the data set on OBA. So for do this, we want to see how the data behaves with different tolerance. So we are going to calculate that matching rate, including all the activity modes, in this case, on bicycle, in vehicle, walking, and still, with tolerance changing every 30 seconds, starting at 30, which takes us from 30 to 3,600 seconds. Those are the steps. So in this case, we are going to have 222. This is not trips, this is records, so this is a typo here, record. And at the end, we're going to have the number of matches. What's interesting here is that the most number of records matches are found in the as expected under the first 350 seconds over here. Okay, so we are going to check over here this point. Sorry, give me a minute. I'm trying to use the pointer here. Okay, so over here in this side. So this is a huge increase during the first 300 seconds, and so we are going to reach almost the maximum rate. In the x-axis, we have the tolerance. So in this case, we are at 3,600. So it is roughly half an hour here. So this is mostly probably after 2,000 seconds, we're going to find those are not necessarily really good matches over here in this area. So similarly, we calculate the error in distances. So we are going to talk about distance and this time. So what is the error in distance? We calculate the detected, the ground truth data position, the geolocation, and we are going to check the location of the match or that we defined before, and we are going to calculate the distance between those two latitude and longitude points. So in this case, again, we're going to have the same data set. We are going to have the 2022 ground truth records, not trips here. And then this is like the kind of well behaved at the beginning under 2,000 seconds, and then the distance is expected to increase after that time, because we're probably going to find matches of different, or we're probably going to induce some error because of time difference. That's the part of the analysis we're working on right now. So what happened then? We're going to check, perform the same analysis, but by mode, because we're going to, the previous analysis was made over the whole data set. So for every mode, for example, we're going to have interesting stuff. Like if we're going to do the analysis only for in-vehicle, then we're going to have only 76 records. Remember, here are not trips, are records for that are only for in-vehicle from ground truth data. So we're going to find here, for example, that the S8, Samsung Galaxy S8 is behaving well here, very well. We almost, like the maximum number of matches is reached before 300 seconds. And then it's also interesting, this part here, that is the S9. S9 is supposed to be, or we were expecting a really, really good behavior. So what's happening? Well, we noticed before, I forgot to mention here, we noticed that the number of records we have for that Samsung Galaxy S9 is roughly half of the other cell phones. So that's probably one of the reasons we are looking at to find that behavior or that bad behavior on that Samsung Galaxy S9, because that's one of the ones we were expecting the best results. So S8 is behaving as expected, is well behaved. And also it is interesting that another cell phone, like a little bit old cell phones, like the LG ones here, are behaving not bad, and in some cases are behaving very well. So similarly, in this case, we did, if we compare in vehicle this matching rate, and we compare the behavior in the average distances, we can notice there is a wide spread here. Like we have different behaviors of what some cell phone behaves way better because the difference in distance is better. In this case, for example, is the Galaxy A01, and the one who's behaving better in performance and in matching rate is, in this case, the SA, but now here it's giving me time difference, distance bigger than the other cell phone, So we did the same for matching the walking. In this case, again, if we compare, if you remember the previous slide for matching for in vehicle, we have all of the maximums around here between 60 and 80%. And in this case, we have other cell phones that are not behaving very well, including the S9. But we already know probably the reason for that S9 bad behavior. But we have now the Galaxy A01 over here, like not behaving so well in number of matches at the beginning. Okay. And similar in the case of walking distance, almost all the cell phones are working in the same range, over 200 meters in distance error for the first 1,500 seconds, which is pretty good, I think. I'm trying to. This is another interesting stuff that we found. For example, in our case, when we went to do this analysis discriminated by on bike, we only found 70 trips, which this is very prone to noise, to be affected by noise. Then every 2 trips, 2 matches is going to do an increment of 10%. So this is, at that point, I think it's not good to use this data from the on-bike yet, but we need to increase the number of records to do a better analysis. So yeah, we can notice that in this case the performance, even though it's different for the different cell phones, they are not like close as in the previous slide, but it's consistent. Like in the S9 is performing, but in this case again, the pixel is start behaving better in this case. So we have different cell phones behaving different in performance in different modes. So that's something that we can bring out of here. This is the same case for on bike, but I'm going to go ahead because something that we need to consider here is the still records. As maybe Sean mentioned before, a still is this time when you are going to do a transition between it's a dual time when in the same location when between two different trips. So there is a noisy, or due to noisy position systems, probably these start and end records aren't going to be the same, and this can introduce some noise, and we noticed that. So we decided to not consider those still records to see how they perform better, if the system performed better. And indeed, we did the analysis again. And this is the same as the first slide, but without the still records. And then we reach over 90% in the case of the S8. And we went from over 70 to over 80, 84, 85% in the first 400 records. So yeah, definitely those records were affecting the accuracy of the whole data set when we are doing analysis over the whole data set. So yeah, that's one thing that we can mention over here. Of course, when we reduce the number of records ground truth data, we need to change that number. We went to 222 to 165. So this means we have like 20% of our ground truth data were still records, which is affecting the accuracy at this point. So this is the same. I'm going to go over here to this box plot analysis is telling some information here. So for example, in this case, we are all the cell phones in the x-axis, and we notice that 70% of the population of the matches mostly are under 120 seconds. That's 2 minutes. So in the case of all of the matches that we found in our case, with what we consider as matches, we have 70% of those matches were found at or under 120 seconds. That's one thing we can take out here. In this picture, we are not showing the outliers. The outliers is a number here out. In this case, we have, for example, we have here 8 outliers. We have here 13 outliers. You know the number of outliers here. Even though it's not a big number of outliers, the big these outliers are we found them like farther away in time when the at the end of the two. Oh, and I forgot to mention. In this case, this is a screenshot used for the tolerance 2010 seconds. We checked that point like a kind of inflection point around 2000, when normally the new matches we start finding new matches that modify the performance over here. So we are doing analysis over this point. This is where we are doing this analysis, or a screenshot for that tolerance. So another take from here is, as I was saying, we have the average here. This green dot is far away from the median, you know, and what's going on. This is data that's affected by the outliers. So even we have a small quantity of outliers, we have outliers that are really, really huge and are impacting the average in the time errors in this case. So I'm trying to go fast, so try to finish in 2 minutes. This is the same exercise, but just for vehicle, and then the behavior improves. So now we have all the data, all the matches under 250 seconds. So we are going to take some about this. We are going to talk about this in the conclusions. and this is a histogram for how the data behaves. So the data, what it's telling me, this histogram is, yeah, definitely, it might at some point, if we have enough data, we're going to find that probably this data at the beginning is going to probably behave as a normal distribution, but since we are going to have those outliers that we're going to find here, so we need to see a way to not consider those outliers or detecting way better at the beginning by doing some tuning on the collection of the OBA, or doing some tuning on the export tool, or doing some tuning, of course, better in the script to detect those matches. So basically, this is the same exercise for a vehicle, and this is going to do the same exercise for walking. I'm going to just go over this because we have roughly 5 minutes, and yeah, I think that I'm going to go with Sean, take away with the preliminary conclusions.
Thank you, Wilson. So you can see that we've been starting to really dive into the data here. So the analysis is still ongoing, so all of these are preliminary conclusions, but what we're seeing so far is that phone models definitely matter. They're similar in some ways, but definitely different in others. The Galaxy S9 really surprised us. It was the newest phone out of the TTI devices, and for some reason, we seem to be collecting much less data from that phone than the others, so we're going to be looking into that further. One note is that all the TTI devices we've been looking at and the data you saw in this presentation, those devices were released April 2017 to mid-2019. The devices we have here at USF are newer, so and that data hasn't yet been analyzed. So when we start adding newer devices with newer hardware, some of these conclusions and graphs could certainly change. A big takeaway is that devices are sensitive. The sensors are very noisy, which is good because they can detect very small transitions. Literally, you standing up from your desk and walking into the next room and sitting down, it will detect that behavior. But when you're trying to zoom back and look at origin destination trips, there's definitely some pre-processing that needs to happen to be able to get to that level. So the current analysis was focusing on the accuracy of activity start time and location accuracy. We still need to look at the ends of the trips to see how similar they are. So filtering out still records definitely seems to reduce some noise in the data set. For the records that do match, as Wilson was showing, the data seems to be relatively accurate. So there was a median activity start time error under 60 seconds. So it does overall seem to be picking up mode transitions pretty well. Some mode transitions seem to be detected much better than others, as Sean had kind of hinted at earlier. So walk, we get the lowest distance error, which also kind of makes sense because you move the furthest or the smallest amount of distance from your location as you're detecting that activity. I think it's also the easiest to detect with sensors. And then bicycle performs the worst based on what we're seeing so far. So our next steps on this project are to finish the collection with the USF devices, which are the Pixel 4a, Pixel 5, and some newer Galaxy, Samsung Galaxy devices. We've tried to automate this matching behavior, or the matching between the ground truth data and the collected data from the app, although we're seeing, there's certain limitations to that because of the noise. So it's just going to take some manual evaluation of the data and matching, I think, to get us to the 100% where we can calculate error for all of the data. So looking at median versus mean as well, those outliers, like Wilson said, definitely seem to be dragging the error up. And then origin destination, we anticipate that destination error is probably lower than origin error because you're staying at that place once you arrive to it versus leaving an origin and then trying to kind of catch up and calculate that error. I think also, investigating the S9 and seeing what's going on there and then further per mode breakdown is important. One last task that we're also going to be doing in this project is talking to stakeholders, so various travel behavior researchers and practitioners, and gathering feedback based on how they think they could use this data based on the accuracy evaluation that we do in this project. So with that, thank you very much, and we're happy to take any questions if we have some time.
Sean, this is Phil. I think Stephanie's having audio problems, so I'll jump in and ask a couple of questions.
Hey, Phil, are you there now?
Yeah, I'm there. Okay.
Okay, I do apologize.
Go ahead. Go ahead.
Okay, so sorry about that. As a reminder, that Q&A box is located in the bottom right-hand corner of your screen. So, Sean, it looks like we have a couple of questions already submitted. That first question comes in. According to the USDOT, commuting accounts for less than 20% of all trips taken. With this data source, is there a way to identify commute trips only? Can we best distinguish trips that are home-based? The origin is the place of residence.
So this is Sean Barbeau. I'll take a first shot at that, and then Sean Turner can jump in if he has something to add. So I think what's interesting about this is there's certainly ways that you can infer that information to look at repeated tours and kind of over an extended period of time, which we do have as part of this data set, potentially months of travel behavior. You can infer home or work-based locations. But because we do have direct contact with the user through the app and via an email address, that's something we could also capture one as kind of a saved trip planning location. So, enter your home address to be able to frequently plan trips to and from that location, or just ask them in a web survey. And I think that would be the easiest way to pick out these commuting trips.
This is Sean Turner. This is how in sync the Seans are, because my answer was going to be the exact same. You would either have to infer it based on where those devices are at the end of the day repeatedly, which is the way a lot of the other data aggregators do it. Or, again, I think the advantage of OneBusAway is you have direct access and you can ask more detailed questions of the OneBusAway users.
Perfect. Thank you. The next question says, can this data accurately detect trip mode, especially biking and walking? I know you briefly touched upon that.
Yeah, absolutely. So this is Sean Barbeau. That's our goal of this project, is to definitively answer that question. I think based on the preliminary data that we have in the analysis, walking, absolutely. It's super sensitive to walking, and we actually, as I was mentioned before, we pick up indoor walking trips that we, depending on what type of analysis you want to do with the data, you may not want, which can be a challenge in eliminating noise. So yes, biking seems to be, based on our, as Wilson said, very small sample size so far. We have a very small number of biking trips. They do not seem to be performing as well as the in-vehicle or walking modes. And I should also note that from the device, we only get an activity transition that's labeled in-vehicle. So one remaining task of either this project or a project following it is to determine if we can infer based on that in-vehicle label whether the person was in a personal vehicle like a car or rideshare ride-hailing service like Uber or Lyft, or if they were in a bus, which is, I think, one of the big questions for transit information in particular. And again, I think we can use some of the in-app information to know to really accurately infer that. But yes, hopefully as a result of this project, we'll be able to answer that question and put numbers on it.
Perfect. And then we're going to ask one more additional follow-up question, because this comes from our NICR partners down in Puerto Rico. They first said that this was an excellent presentation, but then they wanted to know if it would be possible to detect other modes, such as e-scooters, and differentiate them from bicycles.
Yeah, that's a great question, and this is something that we've talked about as well. So we are collecting some scooter share information here in Tampa to try and take an initial shot at this, based on some really early analysis that didn't even end up in this presentation. That scooters are a challenge, I think, because of the low speed and potentially, if you're operating them in kind of shared pedestrian areas, you may have kind of start and stop as pedestrian traffic is near, that makes it look closer to walk or run, something like that. So there is always a possibility of referencing external data sets where, if there's data being shared in like the GBFS format, for example, you could reference and see if a user was near a known location of a shared scooter. So I think it's possible, but we have yet to determine to what accuracy we could do that.
Can you hear me now? Am I there? Okay, thank you.
Yes, Stephanie, yes.
Okay, perfect. Thank you. So again, thank you so much for the great presentation. I did open up the evaluation on your end. Please take a few moments to complete that evaluation, as the feedback provided is very important to the entire NICR webcast series. We do have our next webinar, which is scheduled for October 22nd. Registration is coming soon, so do be on the lookout for that. Again, upcoming webinars, and please feel free to sign up for all of our upcoming newsletters. So again, on behalf of the National Institute for Congestion Reduction, thank you so much, and we'll see you real soon. Bye, everybody.